Hello everyone, and today we are going to learn more about the regression analysis. So this chapter is basically about the linear regression. There would be lots of review, but also we have new materials as well. So if you wanted to go through the book, so this is our book, right? We have experiments. So from this book, chapter 10 mainly covers most of the things that we are going to learn on this topic. But if you wanted to review the background material, the book that we use for the basic statistics. So this is the book that we talked about that before as well. It's Applied Statistics and Probability for Engineers by the same author, Montgomery. If you go to chapter 11 and 12 of this book, it's gonna talk about the regression models. So that's a good option as well. But the thing that we have here and the course note, it should be enough. So let's see what do we have. Okay. Here you go. So a few general remarks. We're gonna review quickly some materials from second year, apply the stats, but also there are new materials, especially on the residual parts and the diagnostic checks. So we are going to learn about some new residuals like PRESS, a more formal and generalized treatment that can be used in any situation like in the course and with any data set. So you would hear these words that I say, like linear least square, ordinary least square, or ordinary regression. So these are regression models that I would call them by this. Just see where is the... Oh, so here are our learning objectives. You want to understand what does it mean when we say fitting linear regression model? You want to understand basic regression model inference, including tests for significance of regression. So test for significance of regression was the time that we would consider, we check to see that if betas, like for the slope, they are equal to 0 or not. Test on individual models parameters, like beta 1, and also the confidence interval. This is the inference that we would have on the parameter. And also another learning objective is that know how to use basic regression model diagnostics, such as residual plots and other types of the residuals that we would have. So I already talked about this. Here is our modeling process that we would use. Basically, it's like that, like in real world, when you want to have your model, you would make some assumptions, like, right, hypothesis, and then you would make your model. Then, as an engineer, you would go and design an experiment. So design experiments, in next chapter, we're going to work on that. It's basically, you're going to intentionally change some parameters in your experiments, and you will then analyze the effect of that on the result. For design of experiments, you would collect the data, do the model fitting, and then diagnostic checks. Whenever we say diagnostic tests, is all of these residual plots and the different types of the residuals, basically. And then we would see that if, like, or R square, that's the result of the residual as well, right? We will see if our model is adequate or not. If it's good, so we would go say that, okay, tentatively we would accept the model. If no, we would, it depends on the situation. We might go and change our assumptions or change our model. We can end up with any of these steps. Why modeling is important? If you want to develop and apply a strategy which would increase productivity. In fact, if you want to have a more efficient model and goes to the optimum point, so you would need to have a good model, right? So we need to consider all of the different valid steps in the modeling for it. We have several levels of mathematical models. You would ask to the model, you would pose question like what if scenarios, right? To simulation of the actual process. The uses of model, it's good for process understanding. Also, it's one of the best way to find out what you do not know about the process. So when you do the modeling, in fact, you would know that because you're going to go to the details of your process. I'm sure you have done that many times so far. It's good for process simulation, like parameter estimation, sensitivity analysis, like most of the inputs of our models, we have fluctuation in the inputs, right? So we want to know that what would be the result on other variables in our process. So we would need to check the sensitivity analysis and also our design. Process optimization, that's good for like surface modeling, process optimization, those ones. Process safety, model-based control. So all of these ones is the usage of the models. Also, it's good for education and training, right, that we do right now. Okay, modeling, it has different stages. When we say modeling, like for example, if we say we have, we talked about that, we have mechanistic modeling and we have empirical modelings, right? So these things that we say is, the reason that we are covering all of this is that just to have a review about the, like for example, what are the states that we would use for our modeling. Step one, understand the process, like the specified process model forms. Step two is going to be experimentation, like data collection. Step three, test models, predictive powers. However, these steps, they can, when you look at it, they can change we can change the order of them as well. And then you want to extrapolate with caution to other operating conditions as well. So as I said, it's like the order can change. We can have iterative procedure from a step 3 back to a step 1, or from a step 4 back to a step 2. And when we are talking about the modeling stage, we would consider that it's sequential, iterative, and we are hoping to reach the optimal result. Okay, so here is the general regression model. It's from the second year. I would quickly go through that. We talked about that in the chapter 1 as well a little. Feel free to ask me questions. We can have like we can have the virtual office hour or like virtual coffee together, a meeting. So basically, this is the regression model, like the empirical model. It's like that you're going to have all of your variables. So here the variables is like x, and then your output is y. So you would say a function like gy is equal to f, like another function based on the like our variables of x, and this theta is like the unknown parameters like beta 0, beta 1, beta 1, beta 0, beta 1, beta 2. So when we say theta star, you might see that I would write down theta or theta star. That's okay if you didn't put the star in your calculation. It's like that it denotes the true value when you see a star, but it's a true value that we haven't reached that yet. So that's the, like for example, you would see I would write down beta 0, I would write down, or beta 0 star. Both of them, they're like true values. But be careful with the, like when we have estimate, like the hat sign that we have on the on top of the parameter. That hat sign, it's very important that you would put it, because it tells me that, oh, you mean that that's estimate. You're looking for the estimate. Epsilon is error. Whatever deviation that you have between the true value and your like the value, between true value and your expectation, like the prediction or the expectation from this model, like what will be the expectation, like the deviation, that's the error. So here is talking about the error, like the source of the errors that we have. We are going to talk about error a lot in this course, and you will see that we have, like, for example, we would say that we have some error that we call it coming from the dependent part of the model, and some of them comes from the independent parts of the model. So the errors that they're coming from the dependent one and the independent ones, we are naming, like they would have different names, like the lack of fit error. So lack of fit error is the coming from the parameters when we are playing with the variables and parameters in our models. So the lack of fit error is going to come up. Then we have another error that we have, the name of it is the pure error. So when pure error comes up, we're going to talk about that later, but it's just to make a bridge right now. When pure error is the time that whenever we have replication, and as I said, we will work on that a lot when we are working with the design of experiment. So with the replication, we would have the pure error, or sometimes when we have the central value in our model, so we would have pure error as well. But the error that we generally talk, like the variance that we generally talk as the MSE, mean square error, from the ANOVA table, is the combination of this pure error and lack of fit error. So because we have different errors, so we would have different source, different types of the source for the errors as well. So here is written that, like, for example, unsuspected value of other independent variable, stochastic factors, lurking variables. All of these are the, like, for example, impurities. That would cause errors as well. Measurement errors. So here we have an assumption is that the independent variables of X, they are perfectly known, which is often not realizable. However, more or less valid if errors in X are much less than error in Y. It's like that. When you affect, like, it's like this. If you have more or less error on your X, it's gonna affect the error of your Y, right? Because Y is depending on X. Now let's look at these ones. You can pause the video here and look at this and see that, okay, so this one is linear, this one is non-linear, this one is linear again, but we have x1 times x2. This one is non-linear, we have x1 over x2, and this one is linear. So we have exponential of x1, x2. So think about it, see if you can find any reason behind it or any connection behind these ones, that why this one is linear, but this one, or this one is linear and this one is non-linear. And then come back and listen to the rest of the video, or watch the rest of the video. The linear and non-linear, when we are talking in a statistic, when we are working with the mathematical modeling, we are interested in the parameters, right? So we want to find out the parameters. When I tell you that y is equal to, for example, beta 0 plus beta 1x, when we are in the statistics, what are we going to do while we are working with regressions? In fact, we are trying to find out what is beta 0 and beta 1. I would say, okay, so when I fit the model, y is equal to, let's say, 5 plus 0.2x. So the parameter that I'm interested to find out while I'm working with regression models are like beta 0, beta 1, and all of the other, like, coefficients. Because of that, when we want to categorize them as linear regression models and non-linear regression models, we need to look at the parameters that we have. So look at here. Here, because the parameter of theta, it's like inside the exponential, so we would say that this is non-linear model. But when you are looking at here, so look at here, how would it's theta 1, okay, so this is linear term, theta 2, this x1, x2, x1, x2, all of these ones, consider them as numbers. Then you want to see that if your model is linear or not. while you are working in the like regression models. So here, theta is like that. You would say, okay, so you have some numbers times theta 4, some numbers times theta 5, another number times theta 6, like your betas, times your coefficients. So it's going to be linear. The next one, you can do the same things for the two others. We have a rule, like you can test it. I'm going to write it down on the board. Let me just show the board to you. So look at here. We say that this is very simple. You just say that, okay, so this is your function. Let's say I wrote down L because we're hoping to have the linear, checking if the model is linear or not. So L, and then whatever you have, if you can say that this one is equal to the alpha, this alpha can be x1 times x2, can be anything. So if you can put the alpha outside the like the function based on theta, you could divide them like this, then you can say your model is linear. Now, if you go back to the slide, let me show it. Okay, so when you go back to this example on page 14 and test it, you will see that, like for the only linear ones, this one is going to work, and for non-linear one, it won't work. Here is the linear regression. So for the linear regression, we talked about that, is the with the model linear in the parameters, and when we say parameters are beta, so here is the beta 1, and the true value of it times f1 x1 plus beta 2 f2 x2. So this is the linear model that we would have. A linear in the parameter model satisfy the, you can get the partial derivative respecting to these betas, and then you can write it in the matrix notation as well. So the matrix Y is equal to the matrix X times matrix beta plus the matrix that we would have for E. And when we have like this one, like you would see that instead of Y, I wrote down here on the, like with the, in the matrix form for all of them. So this Y is going to be like its output that you would have, like your measurement that you would get as an output of your model, like output of the experiments. And then you would have your X are your independent variables. And this, when we are working with the design of experiments, you will see that we play with these X's. And then you would have your beta, that we said is the parameters. So if you look at the dimensions of them, because we have the multiplication, so the dimension should make sense. Like for example, here the dimension is n times p, and then beta is p times 1. So totally is going to be n times 1, right? Like how many variables as outputs that you would have. And then for the epsilons, like any of those variables, they need the any of those outputs, like dependent variables, they would have like their own errors, like residuals. So this is the general form that we would write down. We have some assumptions that we made so far. We would say, okay, the model is valid, the value of the independent variable are perfectly known at each trial, the error are additive to the true value of the quantity being measured, like the Y. They do not co-weigh with each other, they're uncorrelated to each other, the epsilons that we would have, and they are of constant but possibly unknown, but like we would say variance, right? So we can find out these, our expectation for the epsilon is 0. So we had this one before. The variance of the epsilon is the I as matrix that you would have for the identical matrix, and then sigma 2. This sigma 2 has the variance and covariance in it, because we need to consider covariance from now on. And I'm gonna, like in a few slides later, I'm gonna talk about the general equation that we have for the variance and covariance. We have not assumed anything about the distribution of the errors so far, but we will see. Okay, the next video, it's about the estimation of parameters in linear regression models.